The Air Force's legacy in space, an integral part of the story of Brooks, quite literally originated in the stars. The 4 stars, worn by General Bernard Schriever, came to symbolize the Air Force's commitment to what President John F. Kennedy later described as the final frontier. General Schriever set in motion the development of space-based technology that was crucial to launching man beyond Earth's atmosphere. He was instrumental in creating America's ballistic missile program. Known as ICBMs, America's intercontinental ballistic missiles have been our nation's primary nuclear deterrent since the dawn of the Cold War. This weapon system, however, was the genesis for what became a robust Air Force man-in-space program that later supported NASA's early manned spaceflight program. Ballistic missiles, including Atlas and Redstone rockets, were the inaugural launch vehicles NASA used to send astronauts into space. The Air Force's role in space began after World War II. High-altitude aircraft and ballistic missiles parallel development, based on German rocket technology, had led the then Army Air Forces nearer to space. In October 1947, Air Force Captain Chuck Yeager broke the sound barrier in the X-1, the first rocket-powered airplane. To Air Force aerospace medicine pioneer Dr. Harry Armstrong, the X-1 had passed through a much more significant barrier, the line dividing atmospheric flight from space flight. He and his colleagues began to think of spaceflight as a logical extension of high-altitude flight. Their logic also extended to research that would optimize man's survival and performance in space. This research transformed aerospace medicine through the creation of a new subspecialty, space medicine. Air Force space medicine focused on addressing the medical and physiological problems of launching humans into space. In 1947, Dr. Armstrong calculated that it would take more than a decade to solve spaceflight's human physiology problems. That same year, he began to recruit Germany's top scientists and engineers. Dr. Hans-Georg Klaumann was among the first group of German scientists to join the School of Aviation Medicine at Randolph Air Force Base in San Antonio, Texas. Dr. Klaumann was an expert on the mechanics of gas exchange and respiration and a pioneer in weightlessness research. Also joining the school at Randolph were 2 brothers, Drs. Fritz and Heinz Haber. They were renowned experts in astrophysics and aerodynamic engineering, respectively. With these scientists in the fold, and more to follow under the Project Paperclip program, Dr. Armstrong created in 1949 the world's first Department of Space Medicine. This event marked the beginning of the Air Force Man-in-Space program. At the outset, Air Force space science research largely focused on theoretical inquiry seeking to define the problem which future astronauts would face in space. The Space Department's research evolved into practical experiments designed to find out at least tentative solutions to space travel. In this respect, space medicine repeated the evolutionary development that aviation medicine had experienced 35 years earlier. That is, knowledge of the flyer's biological needs and responses temporarily outstripped technology's ability to send them aloft. The pivotal piece of experimental equipment which did the most to bring about Air Force space medicine's evolution into a practical science was the Space Cabin Simulator. School of Aviation Medicine scientists conceived the idea for the space cabin in 1952. Based on Dr. Fritz Haber's design, the first space cabin became operational in 1954. As a modified small pressure chamber, the space cabin created a self-renewing planetary environment. Space cabin experiments' primary purpose was to study human reaction to different gaseous environments. Air Force researchers wanted to determine and validate the most suitable atmosphere for future spaceships. Space cabin experiments at Randolph and later Brooks Air Force Base addressed such important issues as removal of toxic gases and waste. Maintaining a renewable supply of oxygen in space cabins led school scientists to some far-sighted research. Innovative space biology research focused on removing from the space cabin human carbon dioxide waste and replacing it with fresh oxygen. This was accomplished through photosynthesis by growing algae and duckweed in the space cabin's closed ecological environment. These water plants absorb carbon dioxide and produce oxygen. What the early space cabin experiments could not replicate with respect to human physiological reaction were three key conditions of space: acceleration, weightlessness, and cosmic radiation. The Air Force addressed these space conditions through a series of tests and experiments during the 1950s and 1960s. Pioneering acceleration research was Air Force physician-scientist Colonel John Paul Stapp. Dr. Stapp significantly advanced space medicine research in December 1954 when he rode the rocket-propelled sled Sonic Wind at Holloman Air Force Base's 7-mile-long Daisy Track. Stapp became the fastest human on Earth. He survived a deacceleration force of 40 Gs, equivalent to 40 times his body weight.
Getting up to 632 miles an hour on the ground exposed me to the same wind pressure conditions that a pilot would encounter on emerging from a cockpit in an ejection seat at an altitude of 35,000 feet and a speed of 1,000 miles an hour.
Stapp's rocket sled experiments, conducted to study wind blast and abrupt deceleration that pilots experience during aircraft ejections, also contributed to space medicine. The rocket sled test showed that a human, properly positioned and protected, could endure the physiological stresses associated with rapid deacceleration of a spaceship re-entering the Earth's atmosphere. School of Aviation Medicine scientists tackled another great unknown of space, weightlessness, with the same determination and dedication to science that Dr. Stapp displayed in the rocket sled tests. At the forefront of weightlessness research were the Haber brothers. In 1949, they conceived the idea of achieving zero gravity in a jet aircraft by flying a parabolic arc, or Keplerian trajectory. This maneuver created weightlessness for brief periods. At the time, no data existed on weightlessness effects on human physiology.
None of the major effects of weightlessness on humans was really understood. It was a wide open field. We knew, for example, from Mercury, Gemini, that they, post-flight, they lost weight, they were prone to fainting, there was some instability, and that was about the extent of the knowledge.
Air Force weightlessness studies, primarily using F-100 Super Sabre jet aircraft, initially focused on zero gravity's short duration effects.
The real importance, I believe, of those flights was that they were the real first entree into prolonged weightlessness. Remember, 10, 15 seconds, which was, that was the first possibility. Wild and woolly things had been predicted when you placed the human in weightlessness and such. Just the fact that you could be in weightlessness and those things didn't happen was important.
School of Aviation Medicine investigators first conducted parabolic flights at Edwards Air Force Base, California.
Usually there was one of our pilots and an astronaut flying, and the pilot would fly and the astronaut would take the other seat, and they would take it to a certain speed, just under Mach 1, and then they would go into a parabola. And when they done that, of course, the aircraft would go into weightlessness.
These experiments evaluated test subjects' blood pressure, heart and respiration rates, and brainwave activity. The flights evolved into evaluating human consumption of a variety of foods in zero gravity.
The usefulness for food, however, was that I had plenty of room in the back. I had a camera that would record what was going on, and you could do, as I said, 90 seconds of weightlessness, and which is enough time to add water to a container and to open it and to try to eat the food.
Flying parabolic maneuvers from Kelly Air Force Base in San Antonio, the original 7 Mercury astronauts and a host of other test subjects tackled the problem of eating and drinking while weightless.
And they felt that this was necessary because of some flights that were taken in the early 50s in a very small aircraft, because they thought that if the food started floating around in the spacecraft, it could get into instrumentation, it could cause problems for breathing, could be a very significant issue.
These School of Aviation Medicine experiments led to the development of prototype space food feeding systems used by NASA.
So we were looking at the possibility of eating foods using other than the zero-G feeder. And we came up with the idea that if we made food sticky enough, it would be able to be put in a bag or a plate or something of that sort. And we could then perhaps eat it in zero-G and preserve some of the texture of these foods.
Cosmic radiation's effect on human physiology was dramatically addressed through the Air Force's Project Man High program, using high-altitude research balloons.
Well, Project Man High really was the first attempt on the part of the Air Force to conduct research on how to protect a man in space. Dr. Stapp knew we were going to go into space. We had not defined the life support systems, communications, the training of the astronauts, selection of the astronaut. And the way to do this was in a balloon, in a small capsule. And this was Dr. Stapp's first effort to prepare us for the space age.
In 1957, School of Aviation Medicine developed life support and medical monitoring equipment was tested by Air Force Major David Simons. He was suspended in an aluminum capsule from a helium-filled balloon at 19.2 miles above the Earth. Simons had become the world's first spaceman by surviving for 32 hours in the balloon gondola, similar to space cabins planned for manned space flight. He was one of several Air Force high-altitude balloon research pioneers who contributed to space medicine research. Surviving cosmic radiation was only one of the many hazards of space that Air Force research investigated.
Dr. Stapp knew that we would have to get out of the spacecraft to work. That was one of the objectives. Another objective was escape from very high altitude. We had aircraft flying up at 100,000 feet. We did not have a good means of escape. We had had fatalities from high altitude escape. So that was the other objective, was to do research on escape from high altitude.
In a prelude to the first spacewalk, Air Force high-altitude pioneer parachutist Joe Kittinger braved cosmic radiation and minus 104 degrees Fahrenheit when he made his world record-setting parachute freefall from a balloon.
And in 1960, on the 16th of August, I went up to 102,800 feet and jumped. I free fell for 4 minutes and 37 seconds. And when I got on the ground, my team surrounded me and we were elated because we had demonstrated what we set out to do.
Air Force high-altitude balloon flights advanced life support system development and proved that cosmic radiation would not be a problem to man in space.
I didn't want anybody to think that we were doing it to set a record, because we were doing it to gather information we needed for the space program. And that was very important to us. The escape system that were developed on that program back 50 years ago is still being used today. Every ejection seat around the world used a small drogue chute for stabilization to get it down to lower altitude.
The ultimate goal of the Air Force's pioneering space research program during the 1950s was to give the United States the capability of putting a man in space for at least 24 hours and return him safely to Earth. Unfortunately, this ambitious goal was co-opted on October 4th, 1957, when the Soviet Union launched Sputnik, the world's first artificial satellite. America turned to the Air Force for a similar, if not greater, space achievement. School of Aviation Medicine scientists at Randolph Air Force Base provided a dramatic response. Launch a 23-year-old airman from the Bronx, New York, on a simulated trip to the moon. The bold experiment involved sequestering Airman Donald Farrell in a 3x5-foot space cabin simulator for 7 days. Nicknamed Torella-1, or Little Earth, the furnace-like pressure chamber that became Airman Farrell's lunar vehicle was the original space cabin that the school had used in its inaugural simulation experiments in 1954. Farrell's trip, which began February 10, 1958, on the 10th anniversary of space medicine's inception, would be the longest simulated spaceflight conducted in a hermetically sealed chamber with recyclable air. Farrell was subjected to a series of psychological, physiological, and performance tests that measured fatigue, alertness, judgment, and mood. American prestige and the fate of the Air Force Man in Space program rested on the broad shoulders of a confident and cocky young man, and the expertise of school scientists to meet his space voyage needs during the 168-hour flight. The world watched as Farrell successfully completed his simulated moon mission on February 16, 1958. Waiting to congratulate Farrell when he emerged from the space cabin was Lyndon Johnson, the first chairman of the U.S. Senate's new Space Commission. In the Cold War era space race rhetoric of the time, Johnson told Farrell that he had given America its greatest hope for peace in the world. America had finally taken a small step in the space race, thanks in large measure to Air Force ingenuity. The Air Force had hoped that the enormous press coverage given to Farrell's moon journey would bolster its claim over similar initiatives by the Army and Navy to be the federal agency most qualified by experience and technical knowledge to manage America's emerging space exploration program. However, Congress ended the debate on July 29, 1958, when it passed legislation creating the National Aeronautics and Space Administration. As the world's first civilian space agency, NASA was authorized to take over and administer any scientific space plans or systems then under development by the military services. It also had the authority to use the Armed Forces facilities, resources, and personnel needed to carry out the space agency's programs. NASA quickly exercised its authority by taking over the most ambitious space research program, an Air Force Man in Space project to launch a manned satellite into orbit. Rechristened Project Mercury, it became NASA's bid to overtake the Soviet lead in space exploration. Announced in January 1959, Project Mercury resulted in the selection of the first 7 astronauts, 3 each from the Air Force and Navy and 1 Marine. However, NASA did not have or plan to develop the medical capability to support a man in space program. In NASA's early years, the space agency depended upon the Air Force, specifically the School of Aviation Medicine, to provide the space medical expertise to support NASA's programs. Air Force expertise, especially in the life and behavioral sciences, had been consolidated at Brooks Air Force Base as a result of General Schriever's support for the Air Force Base medicine research. He was the driving force behind the creation of the Aerospace Medical Center at Brooks. The center's cutting-edge aerospace medicine and space medicine research provided the incubator for scientific innovations that America relied upon during NASA's early years. The Aerospace Medical Center became a reality in May 1957, when ground was broken at Brooks Air Force Base. The original concept, conceived in 1946 by Dr. Harry Armstrong, was to create a diagnostic, research, and teaching venue dedicated specifically to the medical problems of military aviators.
Well, the idea of AMD was to consolidate all medical research for aerospace medicine, which the term was developed there, aerospace medicine. The department was developed there, and everything came together with that.
By the time the School of Aviation Medicine moved from Randolph Air Force Base to Brooks Air Force Base in 1959, this concept had evolved to encompass space medicine research support to NASA. At a cost of nearly $29 million, this sprawling aerospace medical center complex of laboratories, research shops, and academic facilities were originally designed to support Air Force aviators' aerospace medical needs. The Brooks Center, however, morphed into one of NASA's primary space research and development sites. NASA relied heavily upon the Air Force's space medicine capabilities. NASA hired School of Aviation Medicine scientists to perform research relating to manned spaceflight medical issues. The school's Department of Space Medicine focused on a set of ambitious research goals relating to the protection of astronauts from the harsh, unforgiving environment of space. On a contractual basis, the school supported NASA through space cabin simulation experiments, life support system development, spacesuit design, space food development, and astronaut selection and evaluation. Initially, the School of Aviation Medicine completed 3 projects for NASA. The first involved biopack development. Beginning in April 1959, school scientists provided biomedical support for 3 Project Mercury missile launches. Before NASA could launch men into space, tests needed to be conducted that addressed the then unknown effects of weightlessness, radiation, heat, and acceleration on humans. To better understand these risks to man, NASA planned a series of test launches using primates. NASA contracted with school scientists to create a life support system for a rhesus monkey to be used in the first test flight. Dr. Hans George Klaumann, the School of Aviation Medicine's Space Department head, led a school initiative to create the biopack capsule. This device was a miniature spaceship consisting of a hermetically sealed container. The 100-pound biopack was designed to carry a 7-pound monkey into space. The monkey designated for the first suborbital Project Mercury flight was a primate called Sam Space, named after the school that had raised and trained him. The Sam biopack that would house the monkey had everything except one important accoutrement that the primate needed to survive his high-velocity, high-heat, intensive trip to the cosmos. Dr. Lou Bitter, a School of Aviation Medicine physiologist, took the unusual step of asking his wife Edna to develop the world's first space monkey suit.
He came home this one day and he said, "Can you make me something heat resistant that would hold that monkey in the simulator?" And I thought, heat resistant, what? My ironing board cover. So I whipped up, at that time it was called a Hoover apron, piece of material with a hole in it. You put it over the monkey's head and tied 2 sides.
Properly fitted for his flight, Sam Space made history on December 4th, 1959. He was launched in a Little Joe rocket from NASA's Wallops Island Test Center located off Virginia's coast. Just before the rocket's burnout, the escape capsule containing Sam Space was ejected into the Atlantic Ocean. It was recovered by a Navy destroyer. Sam Space survived his ordeal unharmed. The most famous primate flight that NASA conducted was the launch of America's first space chimp, Ham. Trained at Holloman Air Force Base, New Mexico, the 37-pound chimpanzee was a NASA star before he took off aboard the Mercury Redstone 2 rocket in January 1961.
Ham's journey into space differed from the flights of the rhesus monkeys in that the space chimp performed useful work. This was an important follow-on step to the previous primate flights that were limited to space systems tests that had supported NASA's overall objective to determine if primates could survive in space. Ham's spaceflight performance validated space cabin research that the Air Force School of Aerospace Medicine had provided to NASA. Dr. Don Farr.